Okay, can you hear me right? And you can see my screen, right?
Could you speak a little louder?
Okay, yeah. Just get this closer. It's better?
Yeah.
Okay.
It's
Okay.
still louder.
I'm sorry?
It looks, I think you need to face the microphone.
Okay, let me see. Okay, that's better now?
You're
Yes.
good.
Yeah?
Yeah, it's
Okay,
good.
let me know what it was. Okay, so my name is Federico Lopez Armengol. I'm a postdoc here at Rochester Institute of Technology, and today I'm talking about the Handoff package. I'm really talking on behalf of the entire TCAN collaboration. So a bit of motivation, physical motivation, BNS mergers, binary neutral stars mergers are one of the most interesting systems in the universe. They emit a lot of gravitational waves that we actually can detect. They provide very valuable information about high density equation of states, the neutron star structure, and their magnetic fields. And a substantial part of the air process elements are synthesized there. And they're strong candidates for shock gamma ray burst and so on. So these are really interesting systems, but they are so interesting because they involve a great variety of physical processes, as we've been discussing in this workshop. So a realistic simulation of this system, pre and post the merger, it's been unfeasible for a single code. That's why current models focus on a subset of the relevant physics. So on the TCAN collaboration, as we discussed on the previous talks, we accept this physical complexity and face it with a network of codes, and we hand off data consistently among them. That's our main spirit. In particular, post-merger models have been initialized with some simplifications like constant angular momentum, constant entropy, some prescription for the magnetic fields. There are some realistic post-mergers, but they usually inherit Cartesian coordinates from numerical relativity codes, and that's not the best option for evolving the post-merger due to its symmetry. So that's when the Handoff package comes into play. The Handoff package is designed for translating the final output of a code designed for binary neutron stars mergers to the initial data for a code designed for post-merger evolutions. That's the goal of the Handoff package. The codes involved are, as we discussed today, linearized GRMHT for the merger. This is a highly optimized code that can evolve state-of-the-art binary neutron star mergers. It works on Cartesian adaptive mesh refinement grids. And as we've seen, we're working hard on implementing all the relevant microphysics there. On the other hand, for the post-merger, we're using HARM3D, which has been extensively studied in the literature. It's a GRMHT code for arbitrary static spacetimes. Even it handles time-dependent prescriptions for the metric. But it's highly flexible in terms of grids and coordinate systems, so we can really adapt our coordinate system to the dimensions of the post-merger. So let's see how the handoff works. The handoff actually is not a code on its own, it's just a set of routines, within IGN, some standalone script, mainly written in Python, and some routines in HARM3D. So the handoff is a complex set of codes. The basic steps of the handoff are the following. First, we need to get the destination grid where we want to hand off the data. Then we need to interpolate all the metric and MHD primitives from IGN to this new grid. Then we have to work on parsing and arranging the data so it's readable for HARM3D. And finally, we have to initialize HARM3D with this data. A bit more of details on each step. So getting the destination grid. First of all, we need to design the grid based on the symmetries the resolution requirements of the physics we want to capture. We need to implement this grid on Harm3D, and then we are going to dump all the Cartesian coordinates of the center, faces, and corners of every cell of this interesting grid. Finally, after dumping these Cartesian coordinates, we are arranging all this information, all these Cartesian coordinates to a binary file that is readable by the routines in IGM. Then IGM just takes these files, these grid files, and interpolates all the required grid functions to these new positions of the destination grid. We use fourth order interpolation for geometrical functions, which are assumed to be smooth. But we explore with first, second, and fourth order interpolation for MHD primitives because of the appearance of shocks. Finally, the IGM routines just arrange all the interpolated values in every grid function. This is a lot of information, but the routines arrange all this data into a single binary file. And then we move to the next step, which where a standalone script just reads in this very large file and parse the values of the grid functions. It's really important to have a strong and very clear communication between IGM collaborators and who's running this script, because the binary file is written in a given order. And this same script is a Python script, will arrange this data in a new file that is readable by Harm3D. Here we're mimicking a restart file from Harm3D, basically. As we will discuss later, we implement a selective interpolation order for MHD variables, because at some positions, fourth order might be better suited than first order, but in other positions can be the opposite. Finally, we need to initialize Harm3D. We need to set the exact same grid that we dumped in the first step, and we will read in the handed off data after all the rearrangements in the region of the restart file. There are some adaptive routines within Harm3D that distributes the data along the grid, along every cell in every position. And at this point, we have all the relevant grid functions in place in the destination grid, but tensor quantities are still on a Cartesian base. So at this point, within Harm3D, we transform the metric, the velocities, and the potential from Cartesian coordinates to Harm numerical coordinates, this flexible and signed grid. Finally, we compute numerically the connections of the just thread in metric. So that's how the handoff works, and now we are ready to evolve the post-merger or any other system on Harm3D. Let's see some tests. The first test we designed is of Fishbone-Moncrief disks. The test follows like this. We are constructing exactly the same initial data in both IGM and Harm3D, an axisymmetric torus a la Fishbone-Moncrief. And we're just setting a hydro simulation. And we're exploring two different values for the gamma law, for the gamma coefficients in the gamma law equation of state that we are using. We're exploring 4/3 and 2 for gamma. Here there are snapshots of the Fishbone-Moncrief disks as set in Harm3D. After setting the exact same initial data in both codes, we are doing the handoff of the initial data from IGM to Harm3D. We are handing off all the hydro quantities, and we're also handing off the metric. Ham3D knows about the curve metric, but for testing our routines, we are handing off the metric as well. And finally, we are evolving the handed off data in Ham3D and comparing with the pure Ham3D run. Here there are some results on this plot. We can see the relative error in the density. Here is the position of the disk. This plot is on the x-axis of the 3D grid. Here we are computing the relative error between the density handed off and the density computed by Ham3D routines when initializing the disk. We can see that higher order interpolations do a better work at the bulk of the disk, but at the inner boundary, for instance, actually first order does a better work. Outside of the disk, there is a very large error, but this is because of different setting of the atmosphere. So a movie showing here on the top left, we have the Ham3D evolution. Here we have the first order data set, second order and fourth order. And basically see that the disks are very stable on each, for every interpolation order. There is some accretion or some fall of the floor. That's not happening on Ham3D because of a radial dependence of the decay of the floor. The accretion rate on this, the accretion rate of this disk stays fairly small. So we claim that the handoff is working for the gamma equals 4/3 case for every interpolation order. Then moving to gamma equals 2, we found some surprises. We found that the errors of high order interpolation were higher in the innermost boundary of the disk, and these were so severe that we actually couldn't evolve second and third order data sets in Ham3D. The evolution crashed. It crashed around the innermost boundary. We tried to, we thought on why this happened, and it turns out that the density profiles of the disk are pretty different for gamma equals 4/3 than for gamma equals 2. We can see that gamma equals 2 is much more sharp on the boundaries, at the boundaries. So high order interpolation was having trouble there. So here it's a movie for the evolution of the Ham3D gamma equals 2 Fishman-Moncrief disk and the first order interpolation. Remember, the other ones just crashed. So again, we can see that the disk are stable at 250 M. The accretion rate is considerable at the beginning. There is some probably some shock being accreted, but then it converges to the Ham3D value. So from this test, we got that we have to be very careful about the interpolation orders, specifically for the gamma equals 2 case, which is the case that will follow in the next test for VNS. So another test, of course, our most desired system is a VNS post-merger. We are trying to hand off a data set from IGM, and this is working in progress, actually. So the idea of this test is to evolve in IGM an equal mass binary system until merger and until the space-time has reached stationarity. We're using a gamma law equation of state for the neutron stars. And when the space-time has reached stationarity, we're handing off the hydro and geometrical quantities to Ham3D. There is an extra step that we must implement here in this test, that we must boost to the coordinate system of the final black hole frame, which has a given kink velocity because of the merger. Finally, we're evolving the VNS post-merger in Ham3D. To give you a sense of how the post-merger should look like on Ham3D, here is a movie of the post-merger evolution within IGN. Again, this movie is just for the evolution within IGN. There is no handoff here. So we can see that the post-merger is pretty stable, but we also can see a lot of dynamics going on in the atmosphere of the post-merger. Okay, so after doing the handoff, this is what we get in Ham3D. This is the snapshot of the initial data. Here we can see the equatorial plane for the density and a poloidal cut of the density. We recognize the post-merger here, and the density looks fine. But as you can see, the internal energy of the fluid is much more noisy. The atmosphere around the disk is very heated up, and yeah, there is a lot of dynamics going on there. This is a plot of the radial velocity of the fluid, and again, we can see that a lot of dynamics is happening around the post-merger in the flow. I'm insisting on this because this will be the next issue that we will address: how to move to a given clean floor within Ham3D. Here, something I mentioned before. This is the selective interpolation orders for the density and for the internal energy. Here, red stands for fourth order being preferred under the other interpolation orders, yellow second order being preferred, and blue first order being preferred. The algorithm for selecting the interpolation order in each position is basically we are comparing the errors, subtracting fourth order and second order interpolation with subtracting first and second order. If this difference is, if the first difference is higher than the second one, we choose second order interpolation. But if the difference between second and first order is bigger than a given tolerance factor, then we keep first order. I can explain that again if there is some interest. So as we can see, fourth order interpolation is being preferred at most of the grid. However, for the internal energy, as we mentioned, that has a lot of noise going on, first order interpolation is preferred around the post-merger. Okay, so let's evolve this system. However, the evolution doesn't look like the IGM movie that I showed before. We can see a lot of dispersion and expansion of the disk. This was surprising for us. This runs for 1000 M. It seems to stabilize, but it's very different from what we see in IGM. So for the last couple of weeks, and we've been working on trying to understand what's happening with this post-merger, trying to compare both codes. These are some profiles at the x-axis for the mass density. So the mass density and the internal energy of the, so the blue curve is the handoff data in its raw format. The brown curve is just the first time step in Ham3D. And the green curve is the floor we set within Ham3D. What we find here that it's surprising is that while the mass density is decreasing around 40 M, the internal energy is staying pretty much constant, and then it's a sharp decrease. So this region in between, where the mass density is low, but the internal energy stays constant, gives rise to very high temperatures and entropy of the outer layers of the disk. And we are very suspicious about this being responsible of the dispersion. In the first test, trying to solve this, we just clean all this noisy region of floor to harms floor. So we are just cleaning the blue curve to the red curve. But the movie looks pretty much the same actually, and what we found is that this is not a great idea because a very high velocity shock appears at the boundary of the remnant. This is the radial velocity of the fluid. So we have included a very large jump in the internal energy, and it's causing this shock on the disk. In the second test, we tried cleaning to a hot floor, and we start discussing on what's a realistic floor for the system, and we tried heating the floor while keeping the low density of it, and the shock disappeared, but now we have a floor that is very out of equilibrium. The final test that I want to show you is producing the same idea of reducing the big jump in the internal energy. But now we are cleaning to harms floor. We are taking all this handoff data to harms floor. But now we are cooling the outer layers of the disk. We are basically for energies lower than 10 to the -7, we are assuming, we are, asking for the entropy to be lower or equal than 10 to the 5. That's why we have this constant entropy here in the outer layers. This actually solved the dispersion problem, but of course it's a very aggressive and a very unphysical cleaning. This was just a proof of concept that we need to better understand how to deal with this region outside of the remnant. Well, actually being part of the remnant, but the outer layers. This is how the evolution looks for this test. So another plot on this region. Just recently, I plotted the enthalpy times the time component of the covariant for velocity, and this quantity is usually used for identifying outflows or ejecta of these systems. And what we found is that actually the outer layers of the disk, according to these criteria, are unbound material and are actually can be considered as ejecta. So we're not sure what to expect from this region. If we should expect it to expand, or we should expect it to stay in place like IGM's evolution. So concluding remarks, the handoff package proved to work for Fishbone-Criff disks, but post-merger handoff requires further care and techniques. We're discussing about how to set a realistic atmosphere for a realistic post-merger. I'm asking if we should discriminate about bound and unbound material and treat them differently. And well, actually something we've been discussing about as well is that IGM is sealing the pressure of the atmosphere, so it's not letting it to heat much. That's not the way in HARM3D. So we are also discussing about if this is the relevant piece of code that is showing this difference between the evolution of both codes. And yeah, then some to do for infrastructure. We still have to test and debug the restart routines for the handoff routes. So that's all. Thank you.
Thank you very much. Please raise your hands to ask questions. Jeremy?
Yeah, thanks, Federico. That's great. Can you just flip back a couple slides to the ones with like all the black plots? Yeah, just like this one with the internal energy and entropy. Yes. Do we have? I mean, I know we must have these same plots for the IGM. And I mean, do we see like where is the divergence happening at the handoff, or is it happening like right after the handoff, or
Yeah,
what's going on?
Let me show you these plots. Yeah, here. Some checks that I included. So here on this plot, we have the pre-handoff data. This is before doing any handoff. These are the green dots. And then we have the handoff data with mixed interpolation orders. Yes,
Okay.
basically the problem in the internal energy within this region seems to be that. So in this region, IgM is imposing the ceiling in the pressure. So there are some very heated cells, but as well as there are some cool cells. So we got all this noise on the internal energy.
So it looks like it's actually right. So it actually is in the interpolation and handoff, because you're taking all of this cold fluid and interpolating it up to higher temperatures when you hand it off.
Yes. Yeah. Actually, the atmosphere shouldn't be relevant. So that's why we're not. At first, at least, we were not concerned about this, because we were thinking that it's very low density, it will not impact the dynamics of the evolution, but we're now starting to think that the atmosphere might be playing a role here.
Okay, thank you.
These are some personal comments as well. I don't know if everybody agrees on the TCAN, so which raised the discussion. Here there is a comparison of geometrical quantities as well. This is alpha.
Okay, we have another question from Zach.
Yeah, just first, this is a really great summary. Thanks, Federico. First, a point of clarification. So it's easier to describe what we're doing as a handoff from IgM to harm, but in fact, the interpolation code, I would say, is not IgM, it's a separate Einstein toolkit thorn. Okay. That in fact is compatible with, for example, Spritz with very tiny modification. It's really just a low-level AMR interpolator kind of thorn that's in the Einstein toolkit. And then I have a question. So the movie you showed, the IgM movie, so yes. I created that, but could you just remind us the IgM movie? Was that the one where yeah, I can see from the title. That's actually one where we froze the metric. So those of you who are wondering yes. What impact just freezing the metric has on the disk, the bottom line, at the bulk of the disk, excluding the atmosphere, which of course is going to be active, it's super low density, you have lots of conservative primitive failures and fixes happening there. You can see that the disk is in a pretty stable state over these timescales. There's constant rotation, even though it's kind of hard to see. Maybe I should have added velocity arrows. There is constant rotation. We're looking down at the equatorial plane of the disk, and so it's there's not really a lot of dynamics going on in this. So this is sort of our goal in handing off, to maintain that level of stability. And I think one thing this presentation might have underscored is that we might want to move more toward a smoother transition where we have transitions, because obviously, even though our codes can handle sharp shocks, it's probably better if we smooth them out a little bit if we're going to do this, cleaning of the atmosphere that we're working on. Mm-hmm. But, yeah, that was just a suggestion for moving forward. Thank you very much.
Thank you.
Okay. We have another question from Ian. Ian, can you ask your question?
So I have two questions. The first one would be, how does the interpolation approach compare to that used by the Llama multi-patch infrastructure? Do you know?
Great question. So it's not using the Llama multi-patch infrastructure. It's using just the bare bones carpet AMR interpolation infrastructure. And yeah, I guess it basically, again, we're taking AMR data, Cartesian AMR data, and interpolating onto this spherical domain from R equals 0 or epsilon all the way out to the outer boundary of the harm grid.
Yeah, I think my question's at a slightly higher level because I remember that the Llama team jumped through a number of hoops as to deciding which frame was best in which to do the interpolation and in which to transmit the data, whether they should be using patch local or a global basis and so on and so forth. So that links to my second question as to whether it makes a difference what order you do your operations in. If you do your translation, your coordinate change to the spherical coordinates before interpolation, if you decompose your variables into radial and polar parts and interpolate those on while still doing that on the Cartesian grid. Have you done any of those tests?
Right, so so the bottom line, here's the basic technique. We keep it all on a Cartesian basis throughout the interpolation, because obviously Cartesian coordinates, they don't exhibit coordinate singularities. And that, I think, is the real benefit of doing it that way. And then we actually have to very slightly adjust the center of our grid because the black hole may not be exactly at the coordinate center due to gauge effects and whatnot. So we do, when we do the interpolation, it's about not x equals y equals 0, but about the black hole apparent horizon centroid position. And that's sort of what the coordinate system that's used. But yeah, I try to, the way I avoid issues with coordinate singularities is simply interpolate only in Cartesian basis, do the coordinate transformations after that. Now, granted, that may introduce some unwanted, right? The Jacobians in that process may mix up potentially some of the errors between the different components, but I think that's going to be inevitable, right? If we did, there's a way of doing this, I know, in the spherical basis, whereby basically you pull out the scale factors of the spherical metric and you interpolate those. But I thought that would be more complicated than we needed for this case. I hope that helps.
Yeah, I have a feeling that from the multi-patch work, both Jonathan Thornburg's old code and also the Llama infrastructure, as you go to larger R, the impact of the scale factors does come in, and so it is easier to do the interpolation if you've already done the local transformation. That of course means you'll have some transition radius, where, as you say, you want to avoid doing that anywhere near the center of the axis. But clearly the fluctuations inside the atmosphere are absolutely killing you there. So I think it might be necessary to avoid that.
Yeah, I think it's becoming, over the past month, it's become clear to us that we're going to need to do something about the atmosphere, and because you can see it's noisy even from the idealized situation where we're just using IGM data, freezing the metric, and continuing the evolution. So yeah, I agree. I think we've got to do something with the atmosphere, and so we're on the right track. I just think we might want to try something a little bit smoother as opposed to a sharper transition. And that
yeah, can I make a comment? I think this is a very interesting discussion. I think we should put a topic for the discussion this afternoon about this atmosphere problem. We discussed that, different codes have different, they use similar or different practices on how to handle the atmosphere. So it would be really nice if we could have a little bit of a discussion on this topic this afternoon. So I put an item in there for the discussion so we can continue. Is that
Okay.
Okay, thank you. There's one more question, David?
Yeah, I had a question also on the interpolation. Maybe it's something too technical, but I will ask the question anyway, and then we can decide whether this is the good time to discuss this. So one issue that I worry about is that if I look at the metric fields at the end of my simulations, especially when a black hole forms, they're typically not stationary. There are still gauge effects and things that are evolving everywhere. So I'm a little bit worried about freezing the metric and continuing the evolution, especially for many orbits of the accretion disk at the end. Is this something that you worry about, or have you thought of a possible solution?
yeah. Yeah. So yeah, Federico, do you want to answer this? Yeah.
No, yes, we thought about that, and we tried it. Well, Sake tried frozen the metric, and it is just. We have actually two movies: the one with the frozen metric and one without frozen metric, and they look pretty much the same. So that's why we're confident about.
Can I?
The metric. Yeah.
Can I add something? Okay, so to answer to David, is this David, right? So I remember we discussed this issue maybe over a year or two ago. I am also a little bit concerned about that, but after some of the tasks that were done by Zach on freezing the metric, I'm a little bit less concerned, but our plan is indeed in their handoff to actually do their handoff at various stages of the evolution and then compare. So do their handoff, earlier after the formation of the black hole, and then wait a little bit later, and then compare the results of the evolution, and this way verify that we are in a good shape in terms of the space handling. So the metric is, of course, in a gauge, an evolving gauge. So, but it's evolving. It's not evolving much, at least according to the test that we have seen from Zach. But yes, this is the plan, to do the handoff at different stages and then compare the evolution.
In
Oh,
addition,
yeah, this sounds like a good plan. Thank you.
Yeah, in addition, we are also outputting the vial scalars as part of the handoff as well, so that we can independently measure the kerrness of the space-time. And we could even look at that at different handoff stages, right? So we could either hand off right here, like at the beginning of the movie you just saw. We could let it evolve with the evolving metric for another 1000 M, for example. Look at the kerrness as well at that stage. And yeah, so in addition to, just doing evolutions with different handoff times, we can also quantitatively tell you, right, this is the kerrness of the black hole, and other various, parameters of the space-time one can measure.
I see. Okay.
Okay, are there any other questions? Okay, so according to the schedule, we're actually